Hi there, on the bench another vintage device, an ADI Electrodyne model OC-25. It's a signal generator, but with a power amplifier. Upon unpacking, I immediately noticed it had suffered transport damage and opened it up. That black square is a hole and supposed to contain an analog meter showing the output current. The meter is still there, attached by its wires, but it was bouncing around inside. The frame or bezel holding it and some of the hardware connecting it to the meter were also in parts, but when I shot this, I had fished those items out already. This is the frame, clearly broken. Epoxy to the rescue to glue the parts back together. Hopefully that will hold. While the glue is drying, I disconnect the meter. First of all, because one of the bolts that were used to hold it has also broken off, and secondly, to see if it has suffered any other damage. The meter was held using these arms screwed into the mounting bolts of the meter, and one of them has come out. More epoxy should fix that. I press the bolt back into the hole and it seems pretty solid already. Sadly, it seems all this work was probably in vain, as the meter is pretty much dead. I'm sending 1.5 amps AC through it and it's just zero. I managed to pry off the front of the meter and gave it a good dose of WD-40. You can see the overflow left as a wet patch on the paper. But after giving it some time to do its magic, the pointer is still not behaving as it should. With nothing connected to the meter, it should go back to zero. That very much tells me that this meter is toast. Same story when sending AC amps through it. Even 3 amps, which should be full scale, does nothing. I started to rummage through my pile of analog meters for an alternative. The only AC amps meter, and therefore the best, I found was this 1 amp AC meter. I measured its resistance, which was about 0.195 ohms. So I used some resistance wire to create a similar resistor and attach it in parallel. This means this meter now has a 2 amp full range. It reads a bit low at the low end, but it's okay on the top end. It will have to do. Here's my DIY shunt resistor on the back. You notice that one end has a bit sticking out. That is because I gradually shortened the resistance wire until the 2 amp full scale was reached. I could have gone for 3 amps, but that would make reading the meter awkward, and the non-linear scale makes drawing a new one tricky. Normally the body of this meter would be too tall to fit through the existing hole, but the meter has this deep notch, and with some tricks it's possible to insert it. I'm not sure if this will be permanent, so I cover the gaps on both sides with white cardboard and use the same bracket system that the original meter used to hold it in place. It looks rather flimsy, and we know that it did not survive rough transport, but for now it holds up surprisingly well. After all this meter trouble, let's have a belated good look at the device itself. I did not find any documentation on this, but it's relatively clear. On the right, the PCB is the actual signal generator. By the looks of it, a Wien bridge oscillator with a double potentiometer for the frequency change. In the middle, we have the power supply with 2 massive caps for smoothing the rectified AC. And on the left is the integrated power amplifier on a massive heatsink. A closer look at the oscillator PCB. The mains power switch is actually a circuit breaker. It holds up to 1 amp but will trip at 1.25 amps. The mains transformer is made in the USA, as are all the other components. Clearly, this signal generator was manufactured in the US. The transformer has 2 primary windings for up to 125 volts each. For the UK, they already have been wired by the previous owner, such that we have 2 115 volt windings in series for a total of 230 volts. The neon indicator on the front panel is connected to one of the 115 volt windings. The secondary has also 2 separate windings, each with a tap in the middle. They have been wired in parallel for more current. A bridge rectifier produces a positive and negative rail that goes to the smoothing caps, while the middle tap of the transformer provides the 0 volt or ground. The smoothing caps are from Sprague and massive, 25,000 microfarad at 40 volts DC. I tested them and they are still good. And finally the power amplifier, mounted upside down so all the electrons fall out, as EEV Block Dave would say. It's made by RCA and is the model HC2000H. While I said earlier there is no documentation, an RCA datasheet for the HC2000H does exist. It's a hybrid op-amp with a Class B output stage, good for 7 amp peak with 30 kHz bandwidth at 60 watts. It even has a short circuit protection. There is a schematic diagram on the HC2000H, and on the right you see the application. Very few external components are needed, and they are indeed pretty much what I see in my unit. With that, it's time to close the unit up and start testing it. By the way, there used to be a half-faded sticker on the box not to operate it without load. The previous owner says it was already there when he got the unit 20 years earlier from a closing down US servo motor test department. I removed that sticker because I don't see why that would be a problem running with no load. Maybe the label was referring to loading the servo motors. The first thing I want to confirm is if any inputs or outputs are earth referenced. This is important to know. For example, if you connect a mains operated scope, which is also earth referenced, to the output and reverse the polarity of your probe, you short circuit the output. Well, unsurprisingly, everything on this box is earth referenced. I have a 10 ohm load connected and the fluke meter is showing the AC current, just in case my replacement analog meter is not working properly. The scope shows the waveform. The output volume is controlled by a 10-turn pot, allowing for very fine adjustments. The generator is set to ×10 range and the frequency dial a tad over 10, so we should be around 100 Hz. It works very nicely, about half an amp at about 104 Hz. Changing frequency works, but those dual pots are in need of cleaning as the oscillations cut out sometimes. I connected the OSC BNC socket to the second channel of the scope, which is the blue trace. As I assumed, this output provides direct access to the oscillator signal before it goes through the volume pot. This makes it ideal for triggering. There's also no big mystery what the purpose of the X-in BNC socket is. As per print on the front panel, I zero the output before changing the range switch to X and connecting X-in to another signal generator set to 1 kHz sine output. And as expected, when increasing the output, I now see a 1 kHz signal on the scope. In other words, I'm using this box now as a power amplifier. And this allows using it with different waveforms like triangle or square and so on. I rather like that it has this feature. It opens a lot of possibilities. Back to using the built-in oscillator. With range set to ×1000 and the frequency knob all the way to the right, its highest frequency is just a tad over 21 kHz. Changing the range to the lowest setting ×1 gives about 20 Hz, but I can get lower using the frequency pot. At the very low end, the output doesn't look very sinusoidal anymore, but raising the frequency to about 2.5 Hz and all is fine again. So the usable oscillator range is between 2.5 Hz and 21 kHz. It's a limitation of the oscillator because using external input, the amplifier has no problems going down to 0.5 Hz and up to 50 kHz or more. To test the behavior with no load, I disconnected the load resistor. As expected, no problems. We have a nice sinusoidal output of almost 10 volts RMS. That doesn't sound much, but nothing stops me from connecting the output to a transformer. In this case, it's a 100 volt audio transformer. Setting the frequency to about 1 kHz. There you go, a nice and stable 310.8 volts AC at 1 kHz, for example for calibration purpose when compared with a second calibrated meter. I changed to a 4 ohm load and now I can raise the output current to 2 amps. I could do more, but that is the limit of my substitute meter. But in any case, this unit is great for testing the current accuracy of meters up to 2 amps. The point is not that I can do 2 amps, but the current can be fine adjusted and is quite stable. When providing the 2 amp max current my substitute meter can handle, the unit draws just 0.26 amps for mains and delivers 15.5 watts on the output. 0.26 amps is a long way off from the 1.25 amp trip current of the circuit breaker, but since this unit originated in the US, it probably was designed for 115 volts and drew double the current. That would be 0.52 amps. With that in mind, I think 2.5 amp output current would be possible, which would also tally with the model number OC-25. This concludes my video on the OC-25 itself, but I have a few more shots on my investigation on the defunct analog instrument. Partially removing the scale allows viewing the interior. To my surprise, it's a transformer with a little full bridge rectifier glued on. I did not expect that, but it makes sense for meters doing AC amps long term where the heat of a resistive shunt would be a problem. I desoldered one of the wires leading from the transformer rectifier resistor conversion circuit to the actual meter. This would allow me to feed the meter directly and thus determining if the problem really was with the meter or the conversion circuit. I tried to feed DC current of various strengths and polarity directly into the meter, but no success. The fact that the digital display on my calibration current source always showed 0 means there is no circuit for the current to flow. Conclusion: the meter itself is broken. No harm then in taking it further apart. The conversion circuit is interesting. A current transformer followed by a rectifier. The DC output is bridged by a 1.9 ohm resistor as a load because current transformers must not be used without load. And then there is a 6.8 ohm resistor in series with the analog meter. I connected my Fluke in DC microamp mode where the original analog instrument was, and then sent as accurately as possible 3 amp AC current through the transformer. 3 amp AC input gives 500 microamp DC output. So the actual analog meter was a DC 0.5 milliamp instrument. Those are much easier to get than AC meters. I could simply reuse this transformer arrangement. The only problem is making a new scale, but I've done that before as well. Tempting, so watch out for part 2. And for the meter itself, I examined it closely and confirmed my suspicion that the top spiral spring broke. At least there is no connectivity between the wire and the top contact of the coil. On this drawing, borrowed from Wikipedia, the spring in question is the front one. The springs serve two purposes. One is to provide a force that puts the pointer back to 0 and against which the coil has to work to produce a deflection. The other is to provide the electrical contact to the moving coil. Clearly, both springs must work for the meter to function. Well, that's it for the Analog Devices Incorporated Electrodyne OC-25. Except for one thing. Can it play music? Of course it can. If you like my videos, don't forget to like and subscribe and help growing this channel. And consider becoming a Patreon. The link's in the description. Thanks for watching.